Okay, so let's move to the fifth section, which is the stress migration. This atomic migration is due to the stress gradient. So, which means we have a chemical potential of the atom, this chemical potential will be the stress dependent. Means when the atoms locate at the stress field, then we need to modify its chemical potential. So this kind of stress gradient will also induce the mass transport. So in order, before we talk the detail of physical concept of the stress migration, then probably I'm going to use this example to show you the presence of the stress gradient. So what we have here is you just try to boil the water. And in the beginning, we are going to fill some water in this water pot, right? And put on this stove and try to heat this waters up. So if we take a look on the wall of this water pot, due to we use this stove, so as you know, if we focus on the wall of this teapot, there's a temperature gradient be acting or be created on this wall, right? The inner part, because you have water, so definitely for sure it will be the lower temperature. Then outer region, you will get a higher temperature. So this wall will be subjected to a temperature gradient on this. So if this, in most of cases, this will be the pure metal, right? So this temperature gradient sometimes, the thickness of this wall is around 1 or 2 millimeter. So probably this temperature gradient will induce atomic flux toward the left-handed side if we assume the heat of transport is positive. And next, my question would be, are there any other atomic flux driven by other parameters? Try to counterbalance this atomic flux. So probably first thing come up from your mind will be, because there's atomic flux push to more atoms move to the inner wall, so that will cause a stress field inside this material. So the stress field probably will try to counterbalance this effect, right? And under these situations, there's the other driving force you need to consider will be the water vapor. The water vapor will generate a force to counterbalance this, or acting also on this wall, so also to counterbalance this effect. Okay, so this is the reason why we say that when you try to boiling these waters, when we don't have the water, means that if you forgot to turn off the stove, after you forgot to turn off the stove, then it means there's no water inside this teapot or water pot. Then that may cause some deformation of this teapot after drying. So the reason for this is you are not going to have a water vapor serving a driving force under this situation. Let's probably only have certain forces directly acting on this wall, so that's easy to deform this water pot. So next, I'm going to show you how to quantitatively formulate the potential as a function of stress field or stress. So what we have here is, based on previous description, you know that we need to modify the chemical potential of the atom in the stress field, right? But how to do that? So now we consider interstitials will cause a pure dilation delta omega. And the chemical potential can become like this. This mu1 actually is the chemical potential of atom A in pure materials and or under no stress field. And we need to modify extra term to, this is extra term induced by the stress field, right? So in order to formulate this one, so probably I'm giving you an example here. Before there's a stress field presented in your material, the chemical potential for atom A will be equals to mu1. But if this material suffer a stress gradient, for example, like we inserted edge dislocation inside these materials, then this region we can expect it will be due to the addition of this interstitial or these atoms, then that will cause a stress field or a compressive region inside these materials, right? Compressive region. Don't forget, this is compressive region. So how about the chemical potential of the atoms located at this compressive region? You will expect it's larger than mu1 or smaller than mu1. I would say because we perform extra work to insert this atom inside this region, right? So the potential of this atom definitely is larger than mu1. So you need to end it extra term because you perform work, right? And this work was used to increase the potential of these atoms. So for this case, the phi will be mu1 plus extra term. So when the atoms locate or under the compressive region, the P is negative. So negative is positive. So anyway, you mu1 plus the extra term. And extra term is a compressive. Is a compressive times the delta omega. Omega is the average atomic volume. Compressive stress times the delta omega. But on the other hand, if we talk about is a tensile stress, tensile region, and the chemical potential will be smaller than mu1, right? So it's minus extra term. So here P is positive, so you use a mu1 to minus a positive term. So if we compress to 3 atoms, the atoms at the no stress gradient region, compressive region, and tensile region, what are their chemical potential? Which one has the largest chemical potential will be atoms at the compressed region, atoms at no stress field, and atoms, the small one, will be atoms at the tensile region, right? Okay, so due to you observe the variation in chemical potential, so the atoms is definitely for sure will move from high chemical potential toward to low chemical potential. So in this case, it will be moved from compressive region toward to tensile region. So you will get the atomic flux. And if we switch to vacancy point of view, the vacancy will flow in the opposite direction from the tensile region toward to compressive region. So in order to quantitatively describe this atomic flux induced by the stress gradient, so first of all, we need to formulate the driving force. The driving force, as we mentioned, as long as you know the chemical potential term, you take the gradient minus gradient, then you know the driving force. So we have a potential, right? Take the gradient and minus, you got the driving force. And just remark, compressive region, compressive stress P is negative, tensile stress P is positive. And now you know the driving force, so atomic flux will be The first one is due to the concentration variation, so you use the minus diffusivity concentration gradient. The second term is due to the stress field, so we use the mobility, concentration, and driving force. And don't forget this is positive. Negatives become positive, so here is also positive, so mobility, concentration, and driving force. Driving force is omega times the stress gradient. So expressed like this. So now we want to give you more idea or more pictures about how atoms move along the stress gradient. So what we have is we have a location directed to the right-hand side, and the vertical axis means the stress. And as you know, compressive stress is negative, so we got a compressive stress here. The larger compressive will be more negative. The smaller compressive stress will be less negative. And the upper portion will be positive term, will be a stress. So the tensile stress. So we use a T to represent it. So now we assume the atomic flux of the atom is moved directly to the right-hand side. So when I hope you can draw in the stress field inside these materials, which can cause the atomic flux move directly to the right-hand side. So probably you will write what? Which means the stress gradient will be positive, right? Positive will be the stress gradient be positive. So can be high compressive region to low compressive region. High compressive region means more negative. C. Move to low, smaller, negative. So be this one to this one, or low tensile to high tensile, or compressive region to tensile region. Okay, so now you have some idea how the atoms moves along the stress field, right? Okay, so I'm giving you an example which happened on the polycrystalline materials. So if we have a polycrystalline material, which means we got many grains, right? So we focus on this grain, and this material suffer the shear force. We got a tau here. It suffer the shear force. And we can separate this tau becomes to this direction and this direction. And also this tau separate this direction and this direction. And this tau separate them this direction and this direction. So based on this idea, if you focus on this edge of this grain, it will suffer the compressive stress. And this will be tensile stress, right? And this will be compressive, this will be tensile. So based on this, the atoms, the mass transport will be from compressive region toward to tensile region. So you got the atomic flux go this way, and go this way from compressive to tensile. So you can expect this edge is going to move toward from this side, and this edge will be moved to. So the geometry of this grain will be changed during mass transport on the stress gradient. And so this is a very famous phenomenon we call the diffusion creep. This mass transport is due to the from the compressive to tensile region is a stress gradient happen inside your materials. But this is a atom's point of view, right? But if you want to switch to vacancy point of view, so we also have a vacancy flux, so all the values will be the same with the atomic flux, but the direction will be total upside directions. So you got the vacancy will be moved from tensile to compressive, okay? So you got this kind of flux. And when you also can remember when we try to write down the vacancy fraction as a function of stress, can be expressed like this, and also is a vacancy formation energy, and because under the stress, so you need to end it extra turn extra work performed on due to this stress gradient, so be minus stress times the omega V. Okay? So the other example here or evidence would be if we have interstitials atoms inside our materials, when this interstitial suffer the stress field, and this stress field will lead or drive this interstitial move from compressive region toward to tensile region. So this is the driving force to drive this interstitial movement or this mass transport of these interstitials. Okay, so today we just ended here. So let's move to lecture 3, diffusion equation and solutions. So give you a quick review. Do you remember this equation? Is what? Is the one we use to calculate or estimate the entropy production rate per volume for mass transport, right? So you got the absolute temperature times the entropy production rate per volume will be equals to flux, atomic flux times the driving force, which is the minus chemical potential gradient. But as you know, the atomic flux is not easy to measure, and also the chemical potential gradient is difficult to measure in our experiments. So here we try to convert it to atomic flux to mobility concentration, and also the driving force here will become expressed like this. Mobility of diffusing atom, concentration of diffusing atom can be easily measured, but however, here the chemical potential gradient is still difficult to measure this directly into our experiments. So in order to get the entropy production rate per volume, we need to do something to convert it or relate it, this chemical potential gradient term, to some parameters, right? Do you have any idea here? So the one actually we learned from the Einstein relationship, the slide to derive the Einstein relationship. We got this relationship between the chemical potential gradient and the concentration gradient, right? They are proportional to each other by this Kt divided by Ca. So now we try to substitute this chemical potential gradient with this Kt divided by Ca times the concentration gradient. So after arrangement, then you will get the entropy production rate per volume can be expressed like K times diffusivity divided by concentration and the concentration gradient squared. So based on this, in order to know, based on this relationship, you know, if you increase the concentration gradient, then entropy production rate per volume will increase in the meantime. And additionally, we also know in order to estimate the entropy production rate, we need to know the concentration profile as a function of time and also location. So this is the reason why we need to formulate the diffusion equation and get the corresponding solutions in mass transport. Diffusion equation actually we derived in previous slide, right? And based on here, you know that the concentration is a function of x location and time. So in order to, as long as we solve this, we get the solution for this diffusion equation, we will know how the concentration of diffusing atoms change with location and time. Then next, we take this concentration part to substitute here, then we can successfully to estimate the entropy production rate per volume. So this is the reason why we need to learn how to formulate the diffusion equation and get its solutions. Okay, so let's move to the outline of this lecture. Will be simply divided into 4 parts. The first one is diffusion equations. The most famous one of diffusion equation to you probably is diffusion equation in mass transport. As long as you solve this equation, then you will get the concentration profile as a function of location and time, right? But don't forget, the diffusion equation can also be performed on the heat transport and also the charge transport. As long as you solve that equations, then you can get a temperature profile or temperature distribution and also the electrical potential distribution as a function of location and time. And if we move back to talk about the diffusion equation in mass transport, the solutions can simply divided into two categories. The first one we call a steady state. Steady state means our concentration profile does not change with time, but we still have a driving force exist in our systems. And non-steady state means the concentration profiles does change with time, and also for sure there's a driving force exist in these materials. So no matter it's steady or non-steady state, both these cases we have driving force. The only difference is whether the concentration profile of the diffusing atom change with time or not. And the third section would be we will talk about the concentration dependent diffusivity. In previous case, actually we assume the diffusivity is a constant, right? So this is why we can, this is how we get this result. We assume this is constant, so we directly take this out and left the second order deviation of concentration respect to x, right? So now, how about if the diffusivity is concentration dependent? How to modify the diffusion equation and its solutions? We will introduce you a very famous analyze method we call the Boltzmann-Montano analyze. And at the end of this lectures, we're going to talk about the anisotropic diffusivity. So far, actually, we still assume the diffusivity in any directions is uniform, is the same, are the same, right? But if you consider different crystal symmetries, I believe you will say the diffusivity should be modified as long as we deal with like tetragonal, triclinic, hexagonals, and so on. So I'm going to show you how to deal with if the crystal structure or material structure we deal with is an anisotropic one. So how to modify the diffusivity. And the most famous case would be what? When you, it's graphite, right? As you know, the diffusivity on the graphite actually is different, right? Because the diffusivity of the carbon alone, one layer, is very faster, right? But layer, the diffusivity between two layers of graphite is smaller, right? So graphite actually is a typical have a anisotropic diffusivity. So let's move to the first part, diffusion equations. Diffusion equations in most of time, probably the first thing come out from your mind will be diffusion equation for mass transport. But it also can be used in heat conduction and also charge transport. So how to get the diffusion equation? Do you remember how you derive the diffusion equation for mass transport? We start from continuity equations. So let's take a continuity equation for mass transport as an example first. Don't forget what's the continuity equation for mass transport. If we have a box, a system, sorry, let me draw something. If you have a box here, or you consider this is a system, doesn't matter. Okay, so the concentration change rate inside this box for sure will be equals to the generation or depletion rate of this mass of this diffusing atoms per unit volume, and plus what? the the the, the flux coming from surroundings. So this is we call a continuity equation, right? The concentration change rate inside this box will be equals to the generation or depletion of these diffusing atoms plus the flux from surroundings. So under this situation, if we assume the generation or depletion means there's probably chemical reaction happens inside these materials, right? So generation means generate inside, let some atoms, diffusing atoms be generated inside this box or be consumed or depleted inside this box. So we assume there's no chemical reaction happens, only transport, mass transport. So we assume there's no source or sink operation. So we delete this term out. So the general form for continuity equation can be expressed like this. And as you know, we talk about mass transport. So the flux part, we will use the minus diffusivity concentration gradient to substitute these terms. And this is the one we call fixed second law. In order to simplify this differentiation equation, diffusion equations, we assume that D is constant. It's not as a function of T, time, and location. So you can directly take the D outside the operator, and this equation will become like this. This is the one we call it is a diffusion equation in mass transport. And this operator, we call it as a Laplacian operator. But as I mentioned before, continuity equation is not only for mass transport, can be also applied for heat transport, right? And charge transport. So you can imagine for the heat transport, the J flux will be the heat flux. And this one, because it is a heat, so it will be the heat, right? So we want to show you the diffusion equation for heat transport and also the electrical transport. So under this situation, we substitute the flux term becomes to heat flux, and current density. And the concentration part we substitute, we change with the heat prevalent and also the charge, the change in the charge. So based on this, the heat dq, right? So can be rewritten become the density, heat capacity, and also dt. Cp dt is the heat, right? But the unit is not prevalent, so we times the density. So you got the prevalent. And this one is based on Fourier's law. You got the minus kappa constant temperature gradient. And we just move these parameters to the right-handed side, and you will get these results. And what we have here is a differentiation equation of T respect to X and T, right? So if you compare with diffusion equation, some people also call this parameter kappa divided by density and heat capacity. This term as a thermal diffusivity. Because this one, people call it as a diffusivity. And when we talk about heat transport, this one, some people call it as a thermal diffusivity. So as long as you solve this diffusion equation, you will get the temperature distribution as a function of time and location. The same idea can be used in charge transport. Regarding to the charge transport Q, here we will use the capacitance times the d phi. And also here will be obey Ohm's law, so we will get a negative electrical conductivity times the electrical potential gradient. And we also move this term to the right-handed side, and we rewrote this equation. We will get this diffusion equation for charge transport or electric transport. And as long as we solve this, we know the distribution of electrical potential, right? And just one remind, Do you remember? The what's the Laplace equation? Laplace equation tell you if you take the second order derivative of phi respect with x equals to 0. This means this is the one equation we call Laplace equation. So if you take these results back to here, then this partial phi partial t equals to 0, right? This means what? The electrical potential distribution does not change with time, and also implying that what? Do we have the electrical potential gradient? Do we? Yes, right? Because let me show you something. In order to satisfy the Laplace equation, the phi equals to constant, right? Constant. Gradient of phi equals constant, so phi can be what? Phi is not equals to 0, right? Phi can be ax plus b. So we do have electrical potential gradient, right? And just a remind, Laplace equation. There's a Laplace equation and Poisson equation. What's the difference between them? Laplace equation means that there's no is related to this one. The electrical potential distribution does not change with time, and this implying that what? There's no charge accumulation in our systems. But if there's a charge accumulation, the one we call is a Poisson equation. Okay, so by the way, I'm just want to this is Laplace equation, also can be used in mass transport, right? Laplace equation, this one equals to 0, so means the concentration partial c partial t equals to 0. That also implying that the concentration profile does not change with time. It's the one you learn, the steady state. Under this situation, we still have driving force, right? We do have a concentration gradient, right? The same idea. Okay, you can think about that. Okay, so now we already show you diffusion equation can be used for mass transport, heat transport, and also the electrical transport. And also, so now we focus on the mass transport part. And don't forget that we have two conditions, right? The one is steady state, the other one is non-steady state, and we want to show you what's the solutions for steady and non-steady state. So before we formulate the answer solutions for both these cases, you need to know the boundary condition and the solution for steady and non-steady state. So don't forget, a steady state means the concentration profile does not change with time. This equals to 0. This t equals to 0, implying that this Laplace equation equals to 0. So we do have a concentration gradient, right? So it's consistent. We have a concentration, we have a driving force, and but the concentration profile does not change with time. That means there's no accumulation of atoms. And for the non-steady state, means the concentration profiles does change with time. And under this situation, we also have a concentration gradient, have a driving force. So let's move to the first one, steady state. Don't forget, the step here is what we want to do. We want to measure the concentration profile to formulate the flux. Then we can get the entropy production rate. This is a final goal, right? Based on measure the concentration profile in your experiments, then you can formulate the flux, right? Because direct measure flux is not easy, okay? So by measure the concentration profile, you get the flux, and then you can calculate the entropy production rate. So now the example we have is a steady state solutions, is a time independent. What we have here is we have a sample L, length L, and the concentration at the left-handed side we call a C0, and right-handed side we call CL. And after a while, we observe that the concentration at two ends does not change with time, so the profiles look like this. So it also implies because this is higher concentration, lower concentration, so the atomic flux move to the right-handed side. So this is your experimental observation, right? So next, as I mentioned, you need to, based on your observation, you find that this is definitely a steady state because the concentration profile does not change with time. Based on this, you got the Laplace equation in mass transport. And also in order to know the flux, we need to know the c as a function of x, right? No t, because t this is steady state, so no t. So we need to know the c of x. So based on this experimental observation, you can formulate the c of x expressed like this. So we take the partial with x. Partial with x, so you got the CL minus C0, and you have a negative, so C0 minus CL. So based on this, you successfully get the atomic flux expressed like this, equals to, actually this is constant flux because C0, CL remain constant, and L is a length, and also diffusivity is a constant. So we got the constant flux in these conditions. Okay, so this is easy, right? You can by measure the concentration profile, you got the flux, and if you find, you also can because you already have a atomic flux, so you can get the entropy production rate prevalent for this conditions, right? For these experiments. Okay, so let's move to the more important and more difficult and complicated one, is the non-steady state. So for non-steady state, how we can get the concentration profile as a function of time and location. So what's the non-steady state? Means there's a driving force and the partial c partial t is not equals to 0, right? So first of all, in order to get this one, we need to identify what kind of material system we're dealing with. Then finding how many driving forces acting on these materials to drive mass transport. Then you formulate the diffusion equation, and with the help of the initial and boundary condition, hopefully you can get the concentration profile as a function of time. So the material system we are going to show you can be simply divided into three different cases. The first one we call a diffusion couple. Diffusion couple means, for example, like you bind material A with material B. This is diffusion couple. And a lot of diffusion happens, and this we call a diffusion couple. And also some people call it a step function. The reason some people call it a step function because when you plot the concentration profile of CB, it's really a step function. And if you try to plot the concentration profile of A, also a step function, right? So let me do this. CA is like this. Step function as well. So the first material system is we call step function, and a lot of interdiffusion happens in between, so we call a diffusion couple. And the second case, some people call it is a surface concentration decrease case, and this one have a limited diffusion source. Due to the source, we deposit a very thin layer on the top of our substrate and allow it diffusion happens. Due to the very thin and limited diffusion source, so we can observe the surface concentration decrease with time. So this we call surface concentration decrease case. And the last one, the third one, is we call a surface concentration fix case. Because the reason for surface concentration of diffusing atoms can be fixed is due to it will be an unlimited diffusion source. For example, like you flow the methane into your furnace. You put a substrate here and flow the methane, supply the unlimited methane gas to serve to be a diffusing atoms. Under this situation, the surface concentration of carbon for sure will be fixed. Okay, and under this situation, diffusion happens, so we can observe the diffusion profile. Okay, so this is the three material systems we are going to deal with. And don't forget here, as long as we formulate the diffusion equation, and with the help of initial and boundary condition, hopefully we can get the corresponding solutions for these diffusion equations.